Hi Kidlets, this is your first video on the sun and fusion and energy production within the sun. Before we talk about the sun, we need to spend just a couple moments talking about how the sun was formed. And in talking about how the sun was formed, we have to talk about how the solar system itself was formed, because they're all formed from the same process. All of the material within the solar system, from the planets to the asteroids to the comets to the Oort cloud to the Kuiper belt, all of the objects within were actually born from the production of the sun and the condensation of the solar nebula. And even though this isn't something that we can see, we can look at the objects that we know, and we can look at what we observe, and using the physical principles that we already have definitions of, like conservation of energy, momentum, Newton's laws of gravity, planetary motion, we can explain most of the things that we can observe with a high degree of accuracy. And we can also apply these things to other planetary systems. We can apply them to molecular clouds, where we see that star production and star birth is happening in areas around something called T-Tauri stars, which are actively producing planetary systems. And the process of defining how our solar system was formed really follows the scientific method. And in the physical realm, in terms of space and earth sciences, all we can do is really make an observation of the clues that we have now. And then we can try and come up with some explanations for how things came to be the way that they are. We can test the things that we can and see if our explanation explains what we can come up with. And if it doesn't work, we go back and we repeat it. So, one of the major underlying fundamental clues of how the solar system was made comes in observations of the orbits of the planets. And there are a couple fundamental principles that we can make some general observations of when we look at the orbits of these planets. And those have to do with their rotational axis or spin axis and the direction of their rotation. So if we take a look at each of these guys, we can see Mercury is spinning nearly upright, the Sun is nearly upright, Venus is tilted, Earth is tilted the opposite way. Mars and Earth actually have a very similar tilt. And then if we expand outward, we can see there's some peculiarities there. We can see that Uranus is on its side. We can see Pluto is on its side. Neptune is tilted pretty highly as well. So although there are some anomalies, most everything in the solar system has the same rotational axis, meaning that they all are generally nearly upright. In general, with two exceptions, all of the planets rotate counterclockwise, which is the same direction that they orbit. So they would be moving in this direction, a left-handed view. They would also be rotating in a left-handed view. And we can see these patterns throughout the solar system. However, we do have some anomalies. We have Uranus and we have Venus that actually rotate in the opposite direction. And we can see that Uranus has this really peculiar tilt. And we can see Venus is slightly off the axis of Earth. And we accredit this to a large asteroid impact, not necessarily Uranus. That's really a peculiarity. And we haven't had any long-term study of Uranus. But in terms of Venus, it is rotating in backwards in relationship to all of the other planets. And that is likely attributed to a large impact early in solar system history. And we can see that most of their rotational axes align with the rotational axes of their orbit as well, except for these anomalies. So if we think about an early solar nebula or a molecular cloud, which we'll come to in the next section, we could think about all of the elements that would have condensed out of there. So if we look here at the temperature, and this would be increasing proximity away from the sun, we can see we start with heavier elements, and as we move further away from the sun, we get carbon-rich silicates, and we get some ices in the form of ammonia, slushy hydrogen, things that we can't have terrestrially because it's not cold enough and not in a high-pressure enough system like the giant planets. But this follows exactly the pattern that we see in the interior planets and comes to define the two different planetary groups we have. So planets of this composition would be the terrestrial planets, so Mars and inside, and planets of these compositions would be Jupiter out to Pluto. And within that range, we have the gas giants, which is what we generally think of the outer planets as, and then the ice giants, which are actually what Neptune and Uranus are. And that boundary, really, that separates those right about here is something called the frost line. You don't generally need to know that. But the frost line or the ice line is thought of as a specific distance where it's cold enough for volatile compounds such as water, ammonia, methane, carbon dioxide, and carbon monoxide to condense into solid ice grains. And we see those on the surfaces of the outer giant planets. Now, if we take that last diagram in terms of composition, and we compare that to the relative temperatures at the time that the solar nebula was condensing and beginning to rapidly rotate prior to it completing nuclear fusion when it is expelling all of these materials that then came to be the planets, we can see that this perfectly aligns. And then right here would be right about where we get that ice line, that frost line, where we start to get more of the ice giant planets. And here would be our gas giant planets. Now, yes, this unit is on the sun, but if we're going to talk about the sun, inherently we have to talk about how the solar system was formed. So the generally accepted idea of how the solar system was formed, and in turn all of the planets were formed, is called the nebular theory, or the solar nebular theory. So this is a flow map showing generally how scientists assume that the solar system was formed and that we came to have the sun that we have. So we can see, where's my lightsaber? Let's go with the green one. So we can see that we started out with our interstellar cloud, or our nebula. Nebulas are areas of gas and dust, known as stellar nurseries where stars are born. Under pressure of gravity, it began to collapse. As it was collapsing due to conservation of angular momentum, you had rapid spinning. That spinning also caused a flattening due to conservation of energy and momentum. That flattening gave us a protoplanetary disk. That disk then began to condense and throwing gases to solids, in which case we then had our metals and our rocks accreting to form our terrestrial planets, expelling the gases and ice to the outer solar system due to temperature, and forming our Jovian planets. So that early sun, when it completed fusion, was able to begin to do this, and we'll talk about fusion later on. So initially, the material that did not accrete or form planets, just like how you would take snow to form a snowball, that's really the best analogy of what accretion is. That material that didn't form planets formed asteroids. Asteroids are really remnants of protoplanets, and other leftover materials were likely expelled out of the solar system completely and formed as comets. 90 to 95% of all comets lie beyond the orbit of Pluto. Most will never come to the inner solar system. Only about 5% are short-term comets, which travel inside the orbit of Jupiter. And that's because Jupiter's strong gravitational field towards the center of the rotational system of energy and of mass within our solar system acts to either throw things out of the system or bring things into the system. So likely out past the orbit of Pluto and out in the Oort cloud, the models all show that there should be a few other planets, somewhere between 5 to 10. We do not have a solar system of 8 or 9 planets. Pluto is still a planet in my world. There's a lot of extra material out there, but due to Jupiter's position and its intense gravity, it was able to expel things out. And also due to its positionality, the asteroid belt that's found between Mars and Jupiter was unable to accrete to form planets because its intense gravitational pull would have prevented that. So you had the pull of the sun on one side, Jupiter on the other, and then you're left with this band of essentially failed small little protoplanets. So here's a little pictorial history here. So we can see that this dense region, and of course this is some false color, this is likely seen in infrared. This would have been a dense region within an interstellar cloud, or areas of gas and dust that exist between stars within a galaxy, would have been compressed by something. So these clouds of gas and dust within the interstellar medium will remain that way unless something happens. So just like Newton's laws say an object at rest will remain at rest, well, a molecular cloud will remain a molecular cloud unless something acts on it in order to cause some sort of condensation and compression. In terms of space, that is generally a shock wave by a supernova. So the death of one star will trigger the birth of another star. So that shock wave will then travel through space, travel through the interstellar medium, causing this gas cloud to condense, and that gas cloud will then collapse. And through that collapse and that rapid rotation, you get heat. And when a star has reached 1,000,000 degrees, it's hot enough to complete nuclear fusion, which is what essentially signals the birth of the star. So we would get this intense gravitational collapse, we would get rotation, we would get condensation, and here we can see that frost line I mentioned where you get the rocky material and the metals that are going to condense out here, and we get the lighter elements that are going to be condensing further beyond that line. And then here we have accretion of our smaller rocky materials. This is just showing some examples. And then here we have that nebular capture of the lighter elements out beyond that. So as we have infalling material, it loses gravitational potential energy. That's then converted to kinetic energy back here in our gravitational collapse. So the denser materials will collide with each other and then cause that gas to heat up. Once that temperature and density gets high enough for nuclear fusion, a star is born. We essentially say a star is born once fusion has happened, once it's reached that temperature enough to fuse together light elements into something heavier. So when that gas cloud begins to spin, you have this random motion that tends to smooth out that cloud. And then due to conservation of angular momentum, it causes that infalling material to spin faster and faster as objects get closer to the center of that collapsing cloud. You then have that flattening during the protoplanetary disk phase. And the solar nebula is then flattened into a disk, and you have collisions between clumps of material that turn those random collisions into an orderly rotating disk that can then get hot enough to complete fusion to become a star. And this is what our sun went through about 5 billion years ago, 10 billion years after Big Bang and the formation of our universe. So this process then explains the order and the patterns that we see in most of the solar system, in the majority of orbits. So we know that that's the way things were, and something had to have happened to those planets that we see as anomalies. Pluto is kind of a special case because it doesn't fit the characteristics of either a terrestrial or Jovian planet. But in terms of Venus and Uranus, there had to have been something after planetary formation to make those rotational axes different from what we see in the rest of the solar system. The interstellar medium, or the ISM, is the area that's located between stars that can then give birth to stars. So this would be huge clouds of gas and dust, otherwise known as giant molecular clouds, that then upon compression and gravitational collapse, these can become huge stellar nurseries and factories where generally huge amounts of stars can be born. So the most famous is the Orion Nebula and the Eagle Nebula located within that. So if you look up at the constellation Orion and you see the 3 belt stars, if you look to his arrow sheath, which is on his left hip, that middle star there is actually a nebula that's producing thousands of stars right now. And if you look up on a clear night with really good seeing, you can actually see that it looks kind of dusty. And with your naked eye, on a clear enough night, you can see that it looks like it's not just one star. You can't see the light of the other stars because they're only visible in infrared, but you can see that it looks kind of murky and cloudy, and that's because you're looking at a nebula that's many, many solar systems across. It's huge. So the ISM, or the interstellar medium, also contains primordial gas that's left over from the births and deaths of many other different stars. So primordial meaning that it's older, so you have elemental hydrogen, you have the elements that were created when the huge explosion we know as Big Bang started the universe. There's also leftover material from expanding shock waves from supernovas, which then carry with it the elements that were in those original stars. So because these molecular clouds then go on to make up other stars and give birth to those stars, all the stars that are within one molecular cloud will have very similar compositions, and we call that a neighborhood of stars. So in terms of our sun has a solar neighborhood in which all of its stars that are in that neighborhood, and its neighborhood is about 10,000 stars, they all have generally the same composition, the same age. They're made up of the same things because it was the same supernova that's shock wave caused our molecular cloud to condense. So generally all the stars you see in the sky when you look up, that's our stellar neighborhood. They were all born at the same time. They're essentially siblings to our sun. So while the ISM contains all of the matter and radiation that's located between stars within a galaxy, a molecular cloud represent portions of the ISM that have the density and the size to actually produce molecules. And most notably, that would be molecular hydrogen, which is a primordial gas. So here is one type of nebula called a reflection nebula that has very few dust grains to scatter the light. So when there's a lot of dust grains, it'll reflect the light a lot. And as we saw in the last slide, we can detect these clouds even though they're visible in infrared, even if they haven't produced any stars, because they're going to distort the light that passes through them. Dark nebula on the other side are named because they have so many dust grains they would actually block light coming through from the other side. So within those molecular clouds we have interstellar dust grains, which are the building blocks of stars, which then are the building blocks of planets. These dust grains account for only about 1% of the ISM, and they align with the magnetic field of it. So we can track these magnetic maps of nebula, and we can then tell where the stars are beginning to form. We can detect these star-forming regions. So here we can see an all-sky survey representing an analysis of some Bok globules, which are generally isolated, pretty small, very dark nebulae that contain some very dense cosmic dust and gas from star formation that may take place. So these are huge indicators that this could be a crucial star formation region. So we're going to be spending a significant amount of time talking about stellar evolution and the two different paths that stars can take. But I want to just pause where we're at with talking about star formation and jump ahead to this real briefly because right here in the molecular cloud, how dense that region is determines the mass of a star that you get. So we have an average star, a sun-like star, which will eventually expand to a red giant. It'll cool off to form a planetary nebula, expelling its outer gases, and cool to a white dwarf, eventually fading away. Very unspectacular death. But the other option for a massive star of something approximately 8 solar masses is a supergiant, a supernova, and two potential outcomes of. Sorry, I had a little audio glitch there. These are the two potential outcomes of a supernova. And the important takeaway here is that this all comes down to the initial mass of the star, which is directly related to the density of those interstellar dust grains within the ISM. So if you have a large density of that, you're more likely to have a massive star, but massive stars are very rare. These only encompass about 5% of the population of stars within our solar neighborhood. But early on in the universe, these populated the majority of them. So those lived very hot, fast, short lives, which then seeded the universe with all of these heavier elements. So we will spend a huge chunk of time talking about that. But I wanted to come back to where we're going because that explains why we were looking at the formation of stars in the first place, because that all determines the type of star that you get. That's it for your first video, guys. I'll see you in class.